Hello! In this short video I'm going to try to show you how to model in maths. Now I'm not a maths teacher, so what I mean by modelling is mainly about worked examples, and I'm going to base most of what I'm teaching you on this book, Craig Barton, How I Wish I'd Taught Maths. And in the book there are 60 pages, so buy the book, it's much more impressive than my video. But I'm going to try and show you what modelling might look like in maths. And this is probably the best book on maths teaching ever written. Anyway, go and sample it on Kindle if you don't believe me and take a look. Okay, so this is a GCSE style question, and all the modelling I'm going to show you comes from this question. Now, bear in mind I'm not a maths teacher and I haven't checked my maths on this, okay? What I want you to do is when I give you a solution, I want you to think, Dominic, that's not quite right, but I know how I would do it if I were going to do it. So freeze the screen if you want to understand what the question is. It's obviously a problem-solving question of some sort because it combines two domains of knowledge. It's looking at algebra and it's also looking at angles within a circle or angles within a triangle. So there are 7 things I'm going to try to teach you. This comes from Craig Barton and it's the underlying principle. Teach the how before the why. And he says this is a typical problem with maths teachers, is that in order to secure understanding, they teach the why, but it's done too early before students know how. So if I take an analogy of tennis, imagine that you wanted to learn how to topspin, or your coach wanted to teach you how to do a topspin lob. If your coach spent quite a while talking about the reasons you would need the topspin lob and where you would use this in a game, that would be useful information to you, but it wouldn't help you in any way to lob. What you need first is to know how to lob, and then you would learn the why much more quickly because you could start moving opponents about with your lob because you'd already know how to do it. And that is a fundamental principle. Teach your students the method, the how, before you teach them the why. So I'm going to show you a series of activities which of course you might change, noticing my lack of maths teaching. Sequencing the method, that will be one way to use an explicit model. Then the rest are about misconceptions, not about the sequence here. So this misconception will be in the operation required, misconception in what the numbers mean, misconception about alternative methods, so students don't realise why one method is actually giving the same result as another method. That comes later in the sequence when you're starting to teach the why. And misconception in order of notation. I'm thinking about things like BODMAS or BIDMAS or whatever it is, where students do things in the wrong order. And then the final problem solving bit, which is not applying prior knowledge. And the crucial thing I'll say about problem solving is that it is not a skill. You cannot teach the problem solving skill. What you have to teach is the knowledge. Then once they've got knowledge, you can do something to try and show students how to think about that knowledge to solve a problem. Right, let's slip in. So here you have various solutions to that question that I showed you at the beginning. Let's zoom in on one. So one alternative you have is simply to cover up aspects of the sequence. You as a maths teacher will know whether to show them just this, whether to show them just this one part of the sequence. So you might just show that on your screen and none of the rest of it, or how much of the rest to show. That's going to be your decision, okay? But as I reveal different boxes, it would be nice to do these one at a time. You will be able to test your students on particular misconceptions. So I don't know what they are, obviously, so I've put these boxes in at random, but you would have a professional view of how these would help students think about the method that you've described and the problem that you've given them. Here is another way. You might decide that actually the problems are all to do with the maths terms, the operations, and you might cover them all up. Or no, you might say, actually, Dominic, that's ridiculous. I'd never cover them all up. I would cover up this one and that one and this one. I don't mind. But that is a really good way to uncover whether your class and your individuals understand what the operations are for and how those relate to the question. Another alternative is to just get rid of the things that I've put in a box and just focus on them. So you might have the or and get the students to simplify this sequence down to that. Or you might want them to have that sequence and work out the answer. That seems a bit conventional to me. So instinctively, I'd think, well, if I give them the answer, take something out of the sequence, maybe that would be a better way to test their understanding. I don't know, but you will know. Then Craig Barton is quite interesting in what he says about mistakes. He says it's really useful to provide models with mistakes in them. That doesn't teach students to make mistakes. It actually teaches students to think really carefully. So I would, you might choose a different number or whatever to put in that place, but you'd choose something that went in its spot to make a mistake. You could reverse the symbol there from plus to minus. This might be a notation thing. I'm assuming there's a reason why x comes before 2x. I don't know though. And so I would move that over here. If that isn't an error in maths, you get the idea of what I mean. You might have a sequence that students are doing in an incorrect order. So that's another way of testing. Then we could look at the alternative methods. Again, you would pick different parts to hide in order to expose what students do and don't know. I've done this like this because I'm assuming that they would understand that everything had to be out of 360, although it might not be. You might keep all the top lines and think actually they won't have a problem with that. But do they understand that everything is out of 360? Maybe I'll remove all of those. I don't know. Or you might decide to show them, why is that the same as that? So you could offer them this with the correct solutions in it and then get them to give you that solution there. Or similarly, mess about with these. However you approach these, what you're asking really are two questions. Number one, what is the key thing that I need to hide in order to test for my students' misconceptions? And so it might only be one box, or it might be more than one. And then my second question, once I've got quite expert students, I'm then going to think, well, okay, now how much can I hide to make it still possible to solve? So I've got two competing agendas there. One where I'm just trying to minimize it and just hide that single telling thing that's going to reveal a single misconception. Or the other one is to really test the class when I can't find easy misconceptions, and I'll remove as much as possible. So with this technique, I sense I'm doing something that maths teachers might think they're doing already. So if you look at a maths textbook, you'll be saying, well, yeah, that happens all the time. That's how questions are sequenced. You give particular values and then you change the question and give new values. Well, that's not what I'm going on about here. I'm actually saying, look, why don't you repeat exactly the same question with different values to see if they understand what's going on underneath? That's much more powerful because the method itself will deliver the right result. So it instantly tells you what misconceptions they've got within the method if they can't do it once the values are changed. If you change the nature of the question to make it more complex, you're not really sure whether it's the complexity that's led to the problem or whether it was the underlying understanding in the first place. So redoing the values in the same question will be much more revealing to you as a teacher, and also much more revealing to the kid. They'll suddenly know, right, it's because I didn't understand what was underpinning the method that my problems have happened. It's not because I didn't understand the new question. Right, my final contribution is to go back to the original question, but this time to add in an extra value. So here I'm going to divide this portion further, and I'm going to call this portion is going to have 1.5x, and this portion here is going to have y in it. Now, you might say, no, that's too complicated, or Dominic, you got the wrong end of the stick. But what you really want to take away from this is, What values would I change and add in order to further test the understanding of my students? Okay, what would I add in to make it more clear to my students what they do and don't know? Now, you might be thinking, Dominic, this isn't going to help. You're just teaching students to remember stuff. So this is a quotation from Daniel Willingham that Craig Barton uses in his book. Understanding is remembering in disguise. In other words, if you memorize the methods and work through them, that will then lead to understanding. Again, that's another way of saying, if you remember the how and keep practicing the how, and then you can be explicitly taught the why. And the why makes sense only after you've got the remembering part, after you've understood the how. If I still haven't convinced you to read Craig Barton's book, here is a list of 10 misconceptions he said that he used to have as an advanced skills maths teacher. These are 10 things that up until 2015 he used to insist were good practice, and now he has utterly changed his mind. And therefore, if you still believe any of these 10 things, it would be really interesting for you as a maths teacher to read his book and see why he's changed his mind. And you might change your mind too. So let me know if that was useful. Good luck and goodbye.